topological representation of lattice homomorphisms.
Thank you very much, Mr. Chairman. Thanks a lot to organizers for inviting me and supporting me also. Thank you for your that you came to my lecture. It is just together with my PhD student Wojciech Bielas, we try to develop the lattice theory and to find a good algebraic tool for proving some topological things. As everybody knows, Boolean algebras are just a good algebraic description of the class of compact and zero-dimensional spaces. But there is a lot of spaces interested for topologists which could not be described in that manner. For instance, continua, I mean that connected and compact spaces. So our idea was to find another way to algebraization of topology. So let me start with some well-known, just to fix some notions. We have a lattice. Lattice is just a set with two operations, always 0 and 1. We can always assume that we have the smallest and the greatest element. And there are binary operations. In other words, we can also, using that definition of ordering, to consider lattice as a partial ordering in which all finite subsets has the lower upper bound and the greatest lower bound. It is, and also again we assume that there is the smallest and the greatest element. Under that very trivial notes, let me mention some examples. First of all, we can consider every family of closed family of subsets of a given set, which is closed under meet and join, together with empty set as a 0 and 1 as a full space. Of course, every Boolean algebra, I mean Boolean lattice, is an example of such an object. Another important examples is the class of topological spaces. If I have a topological space, and then we can consider a lattice of all closed subsets, which will be denoted here by CL of X. If the space is much better, I mean it is the Tikhonov space, I mean T1 space with the property that every point and every closed sets have can be separated by open neighborhoods. Then we can consider the lattice of all so-called zero sets. Zero set is a preimage of a one-point set under a continuous real-valued function. So let me say only about that 4 examples, and then for a topological space, a lattice, a sublattice of the lattice of all closed subsets will be called the base lattice whenever the set of all complements is a base for the topology of that space. So another definitions, a lattice is called distributive, like usually if the following formula holds true, formula of distributivity, and also a normality. Normality is in fact a translation of the normality in topological spaces. I mean lattice is normal whenever it is distributive, and for all elements, disjoint elements, there are another elements with the join is 1, and the intersection to these elements, I mean x and y, are empty. Also, we will assume that the lattice is separative. That means which is distributive, and the separativity property holds true. The same property which is used in the forcing theory when we want to embed a partial order to a complete lattice. Also, we need such a property. I mean, if x is not less than y, then there always exists a non-zero element which is below x and disjoint with y. And trivial facts, let me say a bit about triviality. Every Boolean lattice is normal and separative, completely trivial. For every space, the lattice of all closed subsets is distributive. Even more, every sublattice of a distributive lattice, I mean the lattice of all subsets of a given set, is always distributive. And the third fact, that the lattice of all closed subsets of space is normal, even only if the x is normal, and T1. I mean T1 is always assumed. That means that the one-point sets are closed. And example of a bad example, I mean, if we have an infinite discrete space, then the lattice L of cofinite sets plus 0, of course, is a base, but it is not separative. So not every base will be good for our purposes. Proposition 1. Let X be a compact space. Sublattice L in the lattice of all closed sets is a base lattice. Then L is both normal and separative. It is completely simple, very simple. And the next is also very simple, that it is separative. Third proposition, that if we have a Tikhonov space, then the lattice of all zero sets is both normal and separative. Not difficult, but use some very easy calculation. So that three facts are very useful for us, and of course we use the Tarski's theorem that every centered subset of a lattice is contained in the maximal one, and then we can consider for every distributive lattice L the set of all so-called ultrafilters. That means all maximal centered subsets of L. Elements of ULT of L, it's usual abbreviation, usual notion, is called the set of ultrafilters. And the topology on the set of ultrafilters, so-called Wallman topology, is generated by all the complements of sets of the following type. I mean, U star is the set of all ultrafilters in which U is an element. In fact, it is the original construction of Wallman, and the Czech-Stone construction of the representation of Boolean algebra is just the same. But the construction of Wallman was a bit general, just for ultrafilters in distributive lattice. So definition is not new. Also, the theorem is not new. If L is a distributive lattice, then the Wallman space, the space of ultrafilters, is compact T1 space. It's not necessarily Hausdorff. If additionally this lattice L is normal, then it is compact and Hausdorff. It is a construction of Wallman in 1938, something like that. Very, very old. Remark. The first remark is that if B is a Boolean algebra, then the Wallman space coincides with the Stone space of the Boolean algebra. And another remark that if the lattice is separative, then it is isomorphic to a sublattice of the lattice of all closed subsets of the space of ultrafilters, and that family, oh, I'm sorry, is just a moment. And here, that family is a base for the space. In the representation theorem, we have much more than we have in the Wallman theorem, because not only every Boolean algebra is isomorphic, isomorphic to the Boolean algebra of closed subsets of the topological zero-dimensional compact space, but also, what is very important, morphisms are translated to continuous mappings. Here, the situation is a bit more complicated, namely, if we have a compact, for the first, we have not one-to-one translation, lattices to compact spaces. What is the problem? If X is a compact Hausdorff space and L is a lattice, sublattice of the lattice of all closed subsets of X, is an arbitrary base lattice, then the function given by that formula is a homeomorphism. But let me note that the same compact Hausdorff space can be the Wallman space of several non-isomorphic lattices. To do that, it is enough to consider bases of several size. So, from that point of view, that approach is not good because we have not a direct translation. But on the other hand, by that way, we can describe some other properties of topological spaces. And moreover, we are not restricted to the spaces which are zero-dimensional. And we will show some later with some example how to use it, what is the profit from that situation. But first, it was not so straightforward, one can show that if we have normal lattices, normality was described earlier, and we have a homomorphism between that lattices, then there exists a continuous function from the ultrafilter, from the space of ultrafilters of L, that onto the into the space of all ultrafilters of K, given by the following formula for each ultrafilter, of course. This formula is so good that we have just the functor. Similarly, like in the theory of Boolean algebras, we have a contravariant functor, namely, if we assume that we have 3 normal lattices and 2 homomorphisms from K to L and from L to M, then of course we have also a composition of those homomorphisms, and what happens? It happened that the representation of that morphism into topological space is just the composition of those representation of phi and psi. Of course, there is a contravariant functor, so we have such a direction of it's composed in such order. Of course, if we have the identity, then the corresponding function is the identity as well. And if we have an isomorphism of lattices, then the corresponding homeomorphism of Wallman spaces is also a homeomorphism. And what else? If we have a normal lattices, sorry, just a moment. Yes, here. If we have normal lattices and a monomorphism, just embedding of one to the other, then the corresponding function from the space of ultrafilters of U onto the space of ultrafilters of K is a continuous surjection. It is precisely the same situation like in Boolean algebra. However, for epimorphisms, it is not true. And to do this, let me recall what is the Boolean algebra of regular closed subsets. It is just regular closed means that the closure of the interior again is the set. In that Boolean algebra, union is just the usual union, and the join is just the closure of the interior of the intersection, and complement is like here. So in that Boolean algebra, that algebra is isomorphic to the algebra of regular open sets. So the space is an extremely disconnected compact space, and for every lattice, if we have an epimorphism, then the function is an injection, as I noticed, as I said earlier. But let's look for such an example. Assume we have an infinite compact metrizable space, and we have a natural homomorphism, an epimorphism from the family of all closed subsets of X onto the family of all regular closed subsets given by the following formula. It is an epimorphism, not difficult to show, but the function, the so-called Wallman function from the space of ultrafilters of the Boolean algebra of regular closed sets onto the Boolean algebra of the topological space, Wallman space of the lattice of all closed subsets of X is not an injection, not like in Boolean algebra. Why? Because the lattice RC of X is complete. Then the corresponding Stone space or Wallman space is extremely disconnected, but it cannot. But it's not true for metrizable spaces because of the, for instance, such a simple fact that in extremely disconnected compact infinite spaces they are not convergent sequences. So it is not true that the Wallman duality is the same like the Stone duality. And from some sense, it is even much better because then one can describe much more objects in topology. And perhaps at the same beginning, I should note that the idea is not completely new, because, for instance, by a similar thing, not developed in details, but some elements of that approach, Alan Dow and Klaus-Peter Hart proved that every continuum, I mean compact connected space of size omega 1, not greater than omega 1, is a continuous image of the checksum remainder of the half-line. So it is just parallel to the well-known Parowichenko theorem. For continua, it was not so easy, and it is really, some tricks are just like here, not the theory, of course, all. And another, I don't notice here, our colleague from Prague and now Brazil also used a similar approach, I mean, in some ideas connected, just in the problem concerning to continua. What is the name of that? Oh, yes, yes. Sorry. So I mean that it is hopeful to try to use that idea, that thing to develop just to algebraization of at least some part of topology. Another yet example. In the 70s, there was very known problem by Johannes de Groot, who asked whether it is true that for every compact space there exists a subbase such that every covering of elements of the subspace, there are also always two which also cover. Aleksander theorem says that always there is a finite, but there was a problem whether it is a similar situation like in the segment. Always we have a subbase with that property. Two suffices. It appears that it is not it is not true that only for compact metrizable spaces it is true that always there exists base, in fact subbase, but if we are by base and also a subbase, it is the same. In fact, for metrizable spaces, always such a subbase exists, and it was resolved by Szymański and Strock. And another next results done by Bell, perhaps. Istvan perhaps know much better. There was shown that the checksum remainder of the half-line has not such a property. At least checksum remainder of beta n is not super compact. So always we have some properties which could be described using some bases or sub-bases, which is practically the same. So let me say a bit, have I got 5 minutes? Oh, so very briefly, first a proposition that if we have Tikhonov space, then we have a separative normal sublattice, and the space, the Wallman space, is homomorphic to the checksum compactification. But also we can consider another base lattices, and so we have a definition. Perhaps it is yes. Here, if we have a compact space and a base lattice, then L sub C denotes the Boolean sublattice of P of X which is generated by L, and we have then a Boolean algebra, and then we have a natural embedding of such, not embedding, just a surjection of that space, and then we have the following thing. Every compact space is a continuous image of a compact zero-dimensional space of the same size, which is not, it is trivial, it follows from several other arguments, but by that method we can prove that, perhaps just that diagram will be good, that we have some type of functor, that we can enlarge, cover a topological compact space by a zero-dimensional one, such that we have obtained such type of thing, I mean such a functor. And also the following theorem done by Frink, I mean a description of a Tikhonov space, because not our Wallman spaces are not necessarily compact, so Frink has proved that whenever we have a T1 space and there exists a base lattice in our terminology, which is normal and adjunctive, then X is a Tikhonov space. It is just a characterization of Tikhonov spaces, not using real functions. Adjunction is here given a bit. Here is the definition of that. Another thing well known, we have two Tikhonov spaces that always we have then always we have the ring of continuous real valued functions and C of x and C of y, and the isomorphic ring isomorphic is just such a mapping. This I recall the definition, and one can show. Just we prove the following thing: whenever the C of x and C of y, I mean the set of real valued continuous functions, as rings are isomorphic, then the corresponding lattices are also isomorphic. So using the representation, the Wallman representation, we have the following well-known theorem given by Gelfand, very old theorem, and Kolmogorov. If x and y are compact Hausdorff spaces such that C of x is a ring isomorphic to C of y, then x and y are homomorphic. So also some other results. I should start with a note that the paper is almost published in Topological Implications, joint paper with my pupil Wojciech Bielas. Thank you very much for your attention.
So, are there questions? Comments?
Yes.
There are sometimes in these theorems, like the Gelfand-Kolmogorov, there is also a theorem like that which is about ordered lattices. So, have you considered ordered?
Not. We don't yet. It is just the beginning of some program which I would like to give to my to my co-author, to my pupil. And there are also some other questions. You know, there is in Boolean algebras there is a very important thing. I mean the chains of Boolean algebras, and here it corresponds to inverse limits of topological spaces. So there are also some other possibilities, but it is just
This is
not
actually
yet.
very relevant to some very recent developments in the theory of forcing. If David Asper was here or Matteo Viale, they have done work on forcing axioms using exactly this idea of inverse limits of
Yes.
Boolean algebras
Uh-huh.
as forcing functions.
I
They have
see.
obtained some very new forcing axioms.
So thank you very much for the remark.
Are there other comments, questions? And if not, let's thank the speaker again.
Thank you very much. Thank you for your attention.